Hi everybody, welcome to lecture 23. So I'm going to be answering some of the questions and going over some of the slides from lecture 23, which is uploaded to Google Classroom already. It should say lecture 23, unit 4, part 1. So we're starting unit 4, which is going to be a quantitative subject, and we're going to start it with balancing equations. You did a little bit of balancing equations the first week of digital learning, and so now you're just getting really into it, and from there it's going to keep growing, okay? If you open lecture 23, you're going to see a bell ringer. So that bell ringer is asking you, how does the act of balancing an equation reflect the law of conservation of mass? And we're going to answer that question, but first I just want to discuss what a chemical equation is. And that's on a few of the slides as well, so I'm kind of going over in general what you're going to be seeing in lecture 23, okay? A chemical equation is an equation that resembles a chemical reaction. Remember that a chemical reaction is something that takes place in our universe that requires energy, that will change indefinitely the physical sometimes, but for sure the chemical characteristics of the ingredients that you started with. So in this case, for instance, the ingredients we are starting with are C3H8 and O2. We call these ingredients that we start with reactants. So for instance, when you are baking cupcakes or brownies or a cake and you have eggs and flour and butter, sugar, those would be your reactants. Whatever you make after you've applied energy, so in the case of baking, the energy is the heat, right? The heat you're using from the oven is called a product. So in this case, our products are CO2 and H2O. Reactants convert into products. Reactants are always going to be on the left side of an equation. They are always the substances that you start with. This sign here is called a yield sign. Not yield in the sense of like when we're driving, not yield like stop. Yield as in producing. If I have those ingredients for the cake or cupcakes, then my intention is to yield a cake, right? I have eggs and flour and sugar, and my intention is to yield something out of those reactants. So C3H8, which by the way is propane and oxygen gas yield, once energy is involved, carbon dioxide gas and water vapor. I know that in some cases, you're going to start seeing state symbols as well. So state symbols just mean that we have a little symbol next to our substances to tell us the state of matter that our substances are in. In this case, all of these are in gaseous state. Gas, 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 and gas. Some other state symbols you will see are S, L, and AQ. You already saw a lot of these when we went over bonding. Solid, liquid, aqueous. For now, guys, it's not that important. We're going to ignore it for now. It becomes important later. For now, if they're there, great. If they're not there, don't worry about it. So regardless of whether they're present or not, just ignore them for now, okay? You will not need to know if something is solid, liquid, or aqueous to balance the equation. So I'm going to leave it there since it doesn't matter anyway, okay? Now, if I look at this equation, there's a problem with it. On the reactant side, according to these little numbers, okay? These are the subscripts. I know you're familiar with them because we've been building formulas this whole year. Subscripts tell us how many of each atom is present in a substance. Here, C3H8 tells me there's 3 carbons and 8 hydrogens, and this oxygen tells me there's 2 oxygens. On the product side, however, this carbon, there's no subscript, meaning there's just one. That means that on the reactant side, there are 3 carbons, but on the product side, there's only 1. What's wrong with that? What is wrong is that it looks as if I have destroyed 2 atoms. I went from having 3 carbons to just having 1. According to the law of conservation of mass or matter, right? Anything you and I are made of, anything that is what makes our physical environment, cannot be created or destroyed. It can only be recycled. So this equation right now is wrong because it's suggesting that in order for me to go from propane and oxygen to carbon dioxide and water, I have to destroy carbon atoms, and I cannot do that despite how strong I am. So what I have to do instead is realize that I need to balance the equation. Balancing an equation just means that I'm going to put large numbers. They're called coefficients. I'm going to put large numbers in front of my substances that will hopefully help me get to the same number on each side of the equation, okay? We just answered the bell ringer, by the way. The bell ringer was saying, why does an equation that is balanced represent the law of conservation of mass? And well, if you balance an equation, then what you're proving is that you start with a certain amount of atoms and you end with the same amount of those atoms. You don't destroy them and you don't create more of them. You always have to have the same amount in the beginning as you do in the end. So in reference to our cookies and our baking our cupcakes or cake, if I have eggs and flour and sugar in the beginning, at the end, yes, I have a cake, but that cake includes the same amount of eggs, flour, and sugar that I started with. The difference is those ingredients have been transformed chemically, so they no longer look like sugar and eggs and flour. But in the end of the day, whatever atoms make that sugar, make the flour, and make the eggs still exist in my cake. They're just rearranged in a different order. So I'm going to start this by dividing my equation. I draw a line here to divide my reactants and my products, okay? Here's carbon. Let's see, what else do we have? Hydrogen and oxygen. H and O, H and O. I should have the same atoms here that I do on the other side. If suddenly I had like fluorine on the product side, that would suggest that I created fluorine out of nowhere. I can't just create fluorine. Fluorine has to have existed prior for me to end up with it. So this would be totally wrong. Let's count how many hydrogens we have on each side. On the reactant side, I see an 8 here. So there are 8 hydrogens. I see a 2 for oxygen. On the product side, there are 2 hydrogens. And as for oxygens, there are 2 here, but then there's 1 more over here. So actually I have 2 plus 1, 3 oxygens. Obviously, things are not equal, so that means I'm not balanced yet. I have to include that coefficient I told you about, and I'm just going to erase these gas symbols for now to make some space, okay? So let's consider the carbons. The carbons show that there's 3 on the reactant side and only 1 on the product side. Is there any way for me to put a coefficient somewhere and get 3 carbons on the product side? Yes. If I put a 3 here, this 3 is a coefficient and it acts as a multiplication. So it multiplies against subscripts. 3 times, remember that if it's empty, it's a 1, right? So 3 times 1 means that actually now I have 3 carbons. This didn't just affect carbon though. It also affected oxygen, and I have to take that into account. 3 times 2 is 6, plus the 1 oxygen over here. So actually now I have not 3 oxygens, but 7. Again, I had to go 3 times 2, that made 6 oxygens, plus the 1 oxygen over here, so now that's a total of 7 for now. So I balanced my carbons, but my oxygens are not balanced still, and my hydrogens are still not balanced. There are 8 hydrogens here and 2 over here. Is there something I can do to equal the amount of hydrogens? I can put a 4 here. 4 times 2 gives me 8. So now I have 8 hydrogens and 3 carbons, just like here. And I have to change the oxygens again, because I put another coefficient that's going to affect the oxygens. So let's count again. 3 times 2 gives me 6 oxygens, plus 4 times 1. 4 times 1 is 4. That gives me a total of 10 oxygens on the product side. I'm unequal, but luckily, this O has nothing else with it, so it's going to be easy for me to manipulate it. Is there something times 2 that will give me 10? 5. So now I do have 10 oxygens. Carbon and carbon, 3 and 3. Perfect. Hydrogen 8, hydrogen 8. Perfect. Oxygen 10, oxygen 10. Perfect. Our equation is now balanced. That means that in order for me to combust, this is, as you're going to learn, a combustion reaction, okay? So in order for propane to undergo combustion, that just means using propane as a fuel to make energy, okay? So it's just kaboom in different ways. Propane, 1 mole of it requires 5 moles of oxygen. If you have 1 mole of propane, it requires 5 moles of oxygen, and it will create, or it will produce, it will yield 3 moles of carbon dioxide and 4 moles of water. You balanced the reaction. Good job. Now I'm going to skip a few slides. You're going to see a slide that says types of chemical reactions. I want you to just start getting familiar with those, okay? So that you can understand and be able to identify reactions when you see them. One of them is called synthesis reaction. That just means that you take the reactants, usually there's 2, and you make one thing. You go from 2 and you make 1. In the decomposition reaction, well, it's like it sounds. You take one thing and it decomposes into the other things. In displacement reaction, it just means you have 2 things that switch partners and make 2 other things. Neutralization reaction has to do with acids and bases. Don't worry too much about that. We'll get into that later. And a combustion reaction is like the one we just did. It's when you have a hydrocarbon, and that just means something with carbon and hydrogen. That makes sense, right? Hydrocarbon, hydrogen, carbon. That's my cat making noise. So you have a hydrocarbon reacting with oxygen gas, and it always produces carbon dioxide and water. So just take a look at that slide and try to get an idea of what the different kinds of chemical reactions are. Now, there's another slide that says general rules that are helpful to start with. What this means is you might not need these rules eventually because you'll just get so used to balancing equations, but they might be helpful. So the first one says you can only alter the coefficient of a chemical formula, not the subscript. That is so important. I'm going to show you an example of what that means. Rolly. So in the last reaction, for instance, we had C3H8 plus O2, and we had ended up putting a 5 in front of it in order to get 10 of those oxygens. So what it means by you can only alter the coefficient is, I could have, for instance, said to myself, oh, well, if I need 10 oxygens, then I'll just change the O2 and I'll make it O10. That is not allowed. You are never, ever, ever to touch the subscripts. The subscripts stay as they are. The reason being, if you change the subscript, then you change the formula entirely and it is no longer the thing that you wanted. Rolly, stop. My cat's going crazy. So if you change the subscript, you change everything about the substance and it's no longer what you want. So for instance, O2 is oxygen gas. O10 is not oxygen gas. Sorry, he's being really needy. Look how cute he is. Rolly. He got into dirt, so he has a lot of dirt on his face right now. Okay, so you are never to touch the subscript. You can only manipulate the substances in a chemical equation by putting a coefficient in front of them. Okay, good boy. Come on, be a good boy. Okay, so moving on. We're going to do another chemical equation that is in your slideshow right here. Here we have C6H8O7 plus NaOH yields Na3C6H5O7 plus water H2O. First step, divide it. So divide it between reactants and products. Next step, write out the different atoms that you have. So in this case, we have carbon, hydrogen, oxygen, and sodium. Make sure that those are the only atoms on the product side, and they are. So let's just write them in the same order for the sake of organization. Now, carbon, there are 6 of them. Hydrogen, there's 8 here, but 1 here, so 9. Oxygen, 7 here, 1 here, 8. Sodium, just 1. On the product side, 6 carbons, 5 hydrogens plus the 2 here, so 7 for now. Oxygens, there's 7 here plus 1, so 8. And sodium, there are 3. So just take a look and make sure you agree with that. Now, in that list of ways to help you solve for balancing equations, it says balance metals first. However, try to keep the simplest formula for last. Simplest formula would be the one that has the least amount of chemicals in it. Because obviously, if I put a number in front of this one, it's not only going to affect the sodium, it's going to affect everything in here, and that's changing a lot of stuff. So typically, you want to go for the easiest one. However, in this case, it's actually easiest for me to notice that these two, the sodium here and the sodium here, are not in balance, and I can easily change that. So I'm going to start with that metal, sodium. I know there's 3 here and only 1 here, so I'll put a 3 here. By putting a 3 here, I have changed the sodium from 1 to 3. I've also changed the amount of oxygens I have. 3 times 1 oxygen equals 3, plus the 7 here means I have, oops, I put that on the wrong one, means I have 10 oxygens. Again, 3 times 1 oxygen is 3, plus the 7 means I have 10. 3 times 1 hydrogen means there's 3 of them, plus the 8 here. So 8 hydrogens here, plus 3 times 1, 3. So 8, 9, 10, 11, and that's here. Is there anything else you can do? Consider you've matched these, right? You also have the same amount of carbons. So the likeliness is I don't want to change this one because then I would change the amount of carbons. And I don't want to change this one because then I'm changing once again the sodiums and the carbons. So maybe we need to focus on the H2O, right? There's 11 H's here, 10 oxygens, and 7 and 8. What can I do to change that? Start off simply, okay? Maybe you're not sure right away, so you write a number 2 here to see if you get any closer. Let's see what would happen. You'd have 2 times 2, 4 hydrogens, plus the 5 here, and that equals 9. 9 is not 11, so that must not be the answer. So let's just erase what we've done and go with the next number. Obviously after 2 is 3. Don't just jump to like, I'll try 99. Start simple. So let's put a 3 here. 3 times 2 is 6, plus the 7 here. Oops, sorry, not 7. 3 times 2 is 6 plus the 5 here. That makes 11. 11 and 11. Perfect. Now I'm matching. Let's see if it also helped with the oxygens. We have 7 oxygens here, and now we have 3 times 1, 3 more. So 7 plus 3 is 10. Awesome. We balanced the reaction. A balanced reaction for this reaction means 1 mole of this plus 3 moles of this yields 1 mole of this and 3 moles of water. All right, let's do one more. I'm going to do one that includes some parentheses so that you can make sure you know how to distribute, okay? The distribution rules are the same as they would be in any of your math classes. Let's look, for instance, at one of the last slides that you have, where it shows B2BR6 plus, let me make that smaller. Okay. B2BR6 plus HNO3 yields BNO33HBr. So make sure you see that. It's one of the last slides that you have. Let's make this one a little nicer. Sorry, I'm a little limited on what I have available here, okay? Okay, so once again, divide between reactants and products. So let's divide this here. I have B, BR, H, N, and O. Here we have to have the same, so B, BR, H, N, and O. So go ahead and start by putting the different numbers, right? So there's 2 of these. There are 6 here. 1 hydrogen, 1 nitrogen, and 3 oxygens. Here there's only 1 boron, not 3. This 3 only distributes to what is inside the parentheses. So there is only 1 boron atom on the product side so far. Nitrogen is times 3, so there are 3. And oxygen is 3 times 3, so there are 9. H and Br, there's each just 1 of them. Now you might start seeing some clear relationships of what you can change. What the rules suggest is first see if there's a metal and try and solve for the metal. There are no metals here. There is a metalloid, but let's see if there's something else we can work with first. Leave the simplest substance for last if you can, and in this case, there's nothing too simple other than maybe HBr, so we might leave that one for last. Let's see. Balance nonmetals except H and O. Try to leave H and O for last. So let's see what we can do here. We have 6 bromines on the reactant side. Is there a way for us to get 6 bromines on the product side? Yes, here. So by doing that though, I've changed bromine to 6 and hydrogen to 6. That would mean I would have to change the hydrogen over here as well, right? Because now I have a discrepancy between the hydrogens. So maybe I just go ahead and try to put a 6 here. Now I changed this to 6, but that means I've also changed a few other things. I changed the nitrogen to 6, and I also changed the amount of oxygen, 6 times 3 to 18. So what's left? We have 2 borons still and only 1 over here. Let's see if by putting a 2 here, we get to even everything out. 2 times B is 2. It also affects the N and the O. So 2 times N, 1. 2 times N is 2 times 3. That makes 6 now. 2 times 3 oxygens is 6 times the 3 on the outside. That makes 18. We have everything the same now. So now this equation is balanced. We have 1, 6, 2, and 6. All right, so let's actually do one more. One last one. We're going to do this one, a simple one. You might recognize this as a combustion reaction. It's combustion because, as you see on that slide, you have a hydrocarbon reacting with oxygen to make carbon dioxide and water. Okay, so divide into reactants and products. Write out the different atoms you have. And start to count the amount of atoms. So there's 2 carbons, 2 hydrogens, 2 oxygens, 1 carbon, 2 hydrogens, 3 oxygens. So let's see what I should do first. Okay, I see this discrepancy here, so I'm gonna put a 2 here. And that means now I get 2 carbon dioxides, 2 carbons, and I also change the amount of oxygens to 5. 2 times 2 is 4, plus the 1 over here is 5. What's next? 2, 2, 2, 2, 2, 5. Here's a problem. This oxygen has a subscript of 2. There's no way I'm gonna get 5 oxygens on this side, because in order for me to get 5 oxygens, I would have to put 2.5 as the coefficient. And we cannot have 2.5 of an atom. All coefficients are whole numbers. All coefficients are whole numbers, not halves, not quarters, whole numbers. So that means that this is wrong. I have to start again. Now notice that when we did put that 2 in front of carbon, when I put the 2 here, what I was suggesting was that this has a subscript of 1 in front of it, because I assume there are only 2 total carbons in the whole reaction. When you're stuck like this, sometimes what's easy is to look for the more complicated of the substances and double it. So I'm gonna double this one, since last time it didn't work out when I left it as 1. If I double this, now I get 4 of these and 4 of these. To get 4 carbons, I'm gonna put a 4 here. That gives me 4 carbons, and it gives me 4 times 2, 8, plus 1, 9 oxygens. I've made the hydrogens unequal, so let's see, I have 4 here and 2 here. So I'm gonna put a 2, and that gives me 4 hydrogens, but it also changes the amount of oxygen. So 4 times 2 is 8, plus 2 times 1, 2. So 8 plus 2 gives me 10. Now we have 2 over here, but I can easily get 10 by putting a 5. Good job. So you have 2, 5, 4, 2. A lot of balancing is just trial and error. You're gonna have to start with what you think works, and if you get stuck, you just restart with the next number. And try not to get too far-fetched. Just if you started with 1 and it didn't work, then go to 2, then go to 3, 4, etc. The last thing I want to say is balanced equations do have to be in the simplest form possible. So this is, for instance, the simplest form because there's a 5 here. I can't simplify these numbers since they do not have a common multiple. The 2 and the 4 and the 2 can simplify, but I will not simplify them unless it's because every coefficient can be simplified. So that's why this is the final answer. If I had, for instance, the formation of water, this is the correct balanced equation for the formation of water. We have 4 hydrogens here, 4 hydrogens here, 2 oxygens here, and 2 oxygens here. But let's say that in solving this balanced equation, I actually solved 4H2 plus 2O2 yields 4H2O. And you gave me this as the final answer. This would be wrong because 4, 2, and 4 can be simplified to 2, 1, and 2. So before you give a final answer, just make sure that you're giving the simplest form of all the coefficients, given that all the coefficients can actually be divided by a common number. Again, up here, we couldn't divide every coefficient by a common number because we had a 5, and that kind of didn't allow things to happen. Here we did because 4, 2, and 4 can all be divided by 2 and still give a whole number. All right, guys, I hope that this video helped you. I hope you're being safe. I miss you guys. Have a nice day.